Good morning. We're going to start our unit on triangulation now. And we're going to focus on triangulation from plan view in this unit. There are two basic ways to triangulate, and it's triangulation from plan view or triangulation from elevation view. We're going to focus on the plan view. Now, triangulation in itself is a fairly simple process. And we've looked at that before in geometric construction. So if we take three known lengths, we can create a triangle, not knowing the angles or anything else about that triangle. So what we do in that process is we have two known points, or one line, and we'll label that AB for now. And we have our unknown, which would be point C. Now, we have two lines that go with that. It'll be BC and AC. Now, if I have my known lengths and I set my dividers to that length, and I swing AC from A, and then I reset my dividers to line BC, and I swing that. Where they cross, the intersection point becomes our third point. And we can do this with any triangle. We can split other shapes into triangular shapes to help us do our job, to help us out in doing sheet metal work. So if we had, say, something like a wall, and we need to panel this wall, and we know in construction that it's probably not exactly 90 degrees in the corners and things like that, we can split that into triangles and triangulate, measure our wall, measure the lengths we have. So we have three known lengths, 1, 2, 3, say. If we take those lengths and we transfer them onto a piece of metal by triangulation, we'll make the panel exactly the same as the wall is. Okay, so that's where we sort of use triangulation. But in this chapter, we're more referring to triangulation in pattern development. So we're looking at our layout. Okay, so the basics of triangulation, two known points to create a third, and that's a fairly simple process. Where we run into some difficulties is coming up with the lengths. Okay, and when we start our triangulation process, we don't always have what we refer to as true lengths in our views, in our plan view or in elevation view. And what we look at, let's look at one fitting here that we would typically triangulate, is a squared around. So square, rectangular on one end and round on the other end. And you can see specifically on this one, the way that it's formed is we've done what we call bumping it or kinking it, and it's a series of bends. And if we really look at those bends, it's a whole bunch of different little triangles packed one on top of each other. And we started with this large triangle here, triangle after triangle after triangle. We make the pattern. Okay, that's our triangulation layout. But it's finding the lengths, the true length of these lines, these element lines, that's the hard part. Okay, and that's where we struggle a little bit with triangulation. Now, if we break down a squared around a little further, we come up with something like this. Okay, it's still a square shape and a round shape. And what it is just a sample showing the triangles that make up the fitting. Okay, but it's showing us a full triangle instead of us just looking at the element lines in it that we would have in a part. So this one, we're merely looking at the outside edges, which is what an element line is. I like to think of them as the bends. So this one goes a little bit further. It shows us the base of the triangle, the height, and then the hypotenuse. And the hypotenuse is our outside edge. That's our element line. Okay, so when we look at this fitting, we would have an elevation view like this, and our plan view would be looking down on it, something like this. Okay, and I've drawn on the bottom here what our plan view would sort of look like. We have our round shape, and we have obviously our square outside, and we've drawn in our element lines. So these would be the hypotenuse again that we'd be seeing from the plan view. But when we look at these lines in the plan view, they're much shorter than they appear to be here. Okay, the actual true length of that line is taking that distance, it will not transfer to the same here. Okay, these are not true length. The element lines in the plan view are not true length. Again, look at just the side view, or when we kind of look at the three-dimensional view of it. When we look at these triangles, we can see that we have the base and the height. And you put those two 90 degrees and we gain the hypotenuse, which is what we call the true length, the element line. So let's focus on the base here for a sec. And if we look at the base, we have that distance there, okay, right here. If we flip it to the plan view, there it is there. That is the exact length of the base. Because when we look down on this, straight through, that's what we see is the base length here. So we see that in the plan view. Okay? If we take that base length and put it 90 degrees to the vertical height, because that's the second leg of our triangle, is this vertical here. If we put those two 90 degrees, we get the hypotenuse. So what that tells us is any element line in the plan view, put 90 degrees to the vertical height, we can create the hypotenuse. We can find the hypotenuse. So each of these lines represent the base that we would see here of that triangle. Okay, and the hypotenuse of all of them is our true length. That's what we're going to focus on. That's how we're going to construct our first squared around here. Okay, so we know we're triangulating from plan view. I'm just going to sketch a squared around here. Let's go 8-inch diameter and 10 by 10 with a height of 8 inches. Okay, we might have some other details on this. It might have a collar on it. Might be a small end collar, so we'd crimp it, show the crimp there. Might be S and drive, so we could put some drive hooks in there and our 1/2 inches straight. But that's a typical shop drawing, shop ticket that we would see for our project. And how we choose between either triangulating from plan view or triangulating from elevation view. Elevation view is much, much more complicated and time consuming. So we always try and use plan view. And how we decide that is the base, the top and the base, the two ends. Okay? If those are parallel, which in this case they are, we use plan view. Okay, we're going to triangulate from plan view in this case. If we had one cut on a pitch, maybe the same squared around, we cannot now triangulate this from plan view. And the reason we can't, we talk about this one as a vertical height, and back to our sample here. When we look at that vertical height, it's consistent throughout every single triangle here. Every single element line has the same vertical height. Everything in here, because these are parallel, all the height's the same. It's not here, okay? And there's ways we can go about it, but we're not going to go into those. Okay, for now we're just going to say if the base and top are parallel, if the two ends are parallel, we can use plan view. And that's where we want to go with it. Okay, so I'm going to start by drawing up a plan view of our shop drawing here. Okay, so there's our basic plan view. Okay, I've got my square shape, I've got the round inside. A couple of things we can mention when we look at a squared round. A squared round can only ever be formed in halves. Okay, we can't actually make or form a squared round in one piece. So we always deal with halves. Okay, so we're always going to deal with one side of it, and that's it. And in most cases, we always try and make it so that we have at least one line of symmetry. Okay, so that it's symmetrical in one dimension. This one happens to be both ways. Okay, so it's symmetrical left and right, symmetrical up and down. So each quarter is exactly the same as the last. So what that tells us is we can always work from a half of a plan view for a squared around. Now we may develop one half of a pattern and then cut it out, trace it for our other half, or depending on the line of symmetry, if it is all the way out, not a line of symmetry in either dimension, then we're going to have to actually lay out both sides. In most cases, we only lay out half. Okay, so I'm going to work with the one side of it, one half of it, for our purpose here. Now, if we even work with one half, and let's label this one just to get some numbers here. We said that this one is symmetrical in both dimensions, so we really only need a quarter pattern. Okay, that's the minimum required for it because this quarter would be the same as that quarter. But it really, even though that's a minimum and we can do it from that way, I really recommend doing at least a half pattern, a half plan view. It doesn't take much longer. I mean, there's not much extra drawing there, but it really, really clarifies what we're doing and what we're working with. If we just isolate one quarter, it's hard to really envision what we're looking at. Okay, so I always like to work with a half. And our general rule is round gets numbers, square, rectangular gets letters. Okay, so there's our plan view now with our labeling, and now I'm going to create my element lines. And again, the element lines are there for clarity. They're not essential to make the part or make the pattern. They add in clarity. And what I'm doing, and this again goes to any squared around, and it doesn't matter where the two ends are. They can be all over the place. We're going to take one quadrant of the circle and connect it to a corner of one quarter of the square. Okay, so the lower right in this case all connects to the lower right. Lower left to the lower left. Upper, upper. Each corner, so we could actually have a circle here and a square here, or a rectangle. We'd do the same thing. We'd think of these as quadrants. This one we don't need to divide, but still nonetheless. Anything inside here, we'd have our divisions here, and let's label this lower left. This would be lower left, so all of these lines would come to that lower left corner. And you'll see you start drawing something like that, and it'll actually jump out as a three-dimensional shape once you get the element lines in. Okay, but it doesn't matter where the configuration is, on center or not. Lower right, lower right, lower left, lower left. Okay, that's just a general rule for triangulating from plan view. Okay, so plan view, that's as far as we need it. We know that this corner is a duplicate, so I haven't drawn in the element lines, but I could just draw them back to A and work it that way. But the next thing we want is what we call a true length diagram. Remember we said that any element line from the plan view taken 90 degrees to the vertical height will give us the true length. We're looking for the hypotenuse. So we got a 90-degree corner here now. I can establish the vertical height as here. This was our 8 inches tall. Okay, so vertical height, I got the 90-degree corner. If I put in the element lines from the plan view, that will give us all the hypotenuse. So let's transfer those across. So I'm going to pick up length A1. And I'm going to transfer it over. Now, as I take it off, you want to label it. You have to label here. If we're going to have a whole bunch of lines in here, and if we don't have track of what's what, we're definitely going to lose our spot. We're not going to know what's what. So I label this as a line, and a line has 2 points, so A1. I'm going to take A2 and transfer it in. You'll also find that this gets fairly congested. There's potentially a lot of lines that are going to end up in there. Rotate between the bottom and top of the line, and you can swing that line wherever you need to label it. So I've got A1, A2 so far. Let's go A3. A3, and that's the same line. And remember, we said we have a line of symmetry, so some of these lines will overlap each other. But nonetheless, I'm going to label all of them. A4. Same as A1. That's another repeat. Then we'll go from the B side, B4. Same. Right? We know these are duplicates because our quarters are symmetrical. So imagine flipping this side and overlaying it here. My 1's on the 7, the 2's on the 6, 3's on the 5, etc. So B4 is going to be in this same spot, and so will B7. And on this side, B5 and 6 will be the same as A2 and A3. Okay, so we really only got 2 lines out of there. We have A1 and A2. Everything else are repeats. Then the last one we have is D1. And we'll put D1 in there. D1. Now, how do we know what's a true length in the plan view and what needs to be put into the true length diagram? And let's go back to our sample for a sec to get a visual on that. Okay, and this is part of why we label it the way we do. So we have our squared round. We've got the round end, which we've numbered. We've got the square end, which we put letters on. Okay, when we look at it as a plan view, same thing. We got the round and we got the square, but we can't see a height here now. We've lost the ability to see the height in the plan view. But what we do know is going from a number to a letter, we're going from one end to the other in some way, some fashion. So anytime we're going number to letter, true length diagram. Okay? If we're going number to number, that's a true length. That's one of our step-offs. This truly is the circumference of an 8-inch diameter, and that's 1/12 of that circumference. That's true. That's a true length. So number to number is a true length in the plan view. A to D, we drew it, right? That's a true length. We drew AB. We know that that's a true length. So as we go letter to letter or number to number, it's a true length in the plan view. As we go letter to number, it's not. It has to be triangulated. Okay? There's a few other points on that we'll look at, but at this point we're just going to look at this one here, which that encompasses everything we need to know. That letter to number, we have to find the true length. Number to number or letter to letter, true length in the plan view. Okay, so now we have our plan view complete. We have our true length diagram complete. And now we have all the information we need to be able to produce the pattern. We can move into triangulation now. Okay, so let's do that. Now, squared around, there's a procedure that we always follow. We always start with a baseline that's horizontal. Okay, and AB is going to be my starting point, my starting line, my 2 points, my 2 known points. Because remember, we define triangulation by taking 2 known points, creating a third. So I got a baseline there. There's multiple ways I can start it. I can give myself a point here, and I'm going to label that as A. And then I can take my ruler or my compass, it doesn't matter, but what I need to do is establish my baseline to the length of AB now. So I point that one off. That becomes point B. That becomes my known points now. Okay? Okay, so if we think of our process again, taking 2 known points to create a third, if my 2 known points are A, B, there's only 1 point that connects those 2 to make a triangle. Okay, and if we look at our baseline here and we look at our element lines, and I know I haven't drawn in this completely, but if it would be a mirror image of this one, I would have a line back to here. And you can see the way that these lines go, because everything radiates back to B, everything would radiate back to A, that nothing connects A and B except 4. Okay, that makes a triangle. So our unknown point here is 4. So if we think of these in our true length diagram as hypotenuses, what I can do is draw those in, and again, this just adds in a little bit of clarity. It's not absolutely required, but it starts to show us that if we take the vertical height up against the length of the plan, it will create the hypotenuse. So here's our plan length that we took from our plan view. 90 degrees to our vertical height now gives us the orange, which is our hypotenuse, and we know the hypotenuse in this process becomes our element line, our outside edge. Okay? So let's go ahead and start triangulating. Now that we have all our lengths, it becomes, again, an easy process. We just got to keep track of things is really the key to it all. Okay, so 2 known points to create a third. My unknown is 4 here. So I look at my true length diagram, and I need line A4 and line B4. So I come over to my true length diagram. I look for their match. They're both the same. So I'm going to pick up those lengths with my compass. And there we go there, A4 from A. Okay, same distance because these ones happen to match, right? And B4 from B. That now creates point 4. So we created our unknown. Okay, if we look now back to our plan view, what's the next triangle in order? Now, we can work this pattern both ways because it is symmetrical. So we can work both ways knowing that we only need to really work one side. If I look at B4, as now my two known points, the one point that connects those is 5. 4, 5B is my next triangle. So let's pick up true length B5. And swing it from B. Now again, because we're on a line of symmetry, I'm going to swing it because it's the same as A3. Swing it both ways. Okay, so I've swung true length B5. Now I need to swing 4, 5 because that's the next line that connects the two. So I pick up 4, 5 from my plan view, and remember that's true length, number to number. And from 4, I swing that. And those become point, whoops, wrong way. 5, and that one will be 3. Going this way. Okay, so let's take a few, because my arcs were large, just for clarity, we'll shrink this down a little bit. And we get something like this, right? Okay, what I like to do is, because I still have my 4, 5 on my compass, our next triangle, now that we have B5 complete, is 6. 4, 5, B5, 6 is our next triangle. So our step off, same again. So I'm going to step it off while I still have it set on my dividers. So I just do the step off first, this case, instead of last. And then the next line I need to connect to finish that triangle is B6. B6 is this one here. So I pick up true length of B6, swing it, and my other side as well. That gives us 0.6 here and 0.2 here. So now our known is B6, our unknown is 7. That's the only one that makes the triangle. So we'll take true length B7, which is again stretched out to our long one, and I swing it from B. And A1 from the other side, pick up my 1/12 division, and swing it to complete points 1 and 7. So now we've gone all the way at the top. We've gone all the way around the circumference here. So the top's complete. Okay, but we're not complete at the bottom yet. We need to still create C and D. Okay. Let's keep on this side. C7 we put into here. That one was with D1 because it's our line of symmetry. So we need to triangulate C7, point C7 from our true length diagram, and then BC, which is a true length here. So I'm going to pick up C7 first. Now the last ones we're going from B up, but this line doesn't include B. We can't swing it from B anymore. These are our two options, either swing it from C or swing it from 7. Well, we don't have C yet because that's what we're trying to create. That's our unknown. So that tells us it has to be swung from 7. So I swing it down this time. This is the one line that gets swung downwards. Okay, and it brings in that line, that arc down. Then I can pick up true length BC. and swing it. And that becomes DC. So there's our triangulating done, because we know we've gone 1 to 7 on this side, and we've got all 4 letters included at the base here. Okay, we've gone all the way here now, gone all the way there now. That's the end point. So let's take and fill in that pattern and see how it looks. We do have a way to check our pattern, and that's on what we refer to as the wing here. And that's this last triangle that we made. And the wing on a squared around will be a 90-degree corner. Okay, so I connect, draw on the lines BC and AD, and then up to 1 and 7. And when I do that, these wings, this corner here at point C and point D, should be 90 degrees. Okay, if they're not, you've done something wrong, go back and check it. But that's our check for a squared around. Is that corner 90? Looks pretty good, but I can take my drafting arm and let's put it on there. Perfect. Okay, that's exactly 90. So we've done that correct. Our other checkpoint is at the top. Okay, and because we're using step-offs, and we've talked about the inaccuracy of using step-offs, you can calculate out mathematically your 1/12 and actually get a straight line and use that as your step-off. Excuse me. You can also take a piece of string or something to measure this, okay, at the end. And if we measure it, it should equal a half circumference. So we can check that mathematically as well. Okay, but now we're going to take you're going to use a flexible curve and draw in our arc here. Okay, that should be nice and smooth. If you see kind of a lump or bump in it, again, something's wrong there. And that probably will transfer to out of 90 here, but you never know. But this should be a nice, smooth, clean arc there. Okay, so check for 90s always. Check for a smooth arc. And that's our half pattern. We'll have to cut this and flip it and make another one. Half pattern for a squared around triangulated.